In this video, I introduce a Data2vec multimodal learning framework. Data2vec model uses the same learning method for text, speech, and image. Using self-attention transformer as a multimodal encoding network, Data2vec learns the contextualized latent representations that take entire training example into account. The architecture of Data2vec model is shown here. Data2vec is trained by predicting the latent representations of the full input, give a partial view of the input. Namely, the latent representations of the full input is regressed by the same model based on masked input. The teacher model is parameterized by the exponentially moving average, and the student model predicts the average of the top key layers of the teacher network. The trained student model is used as an encoder for multimodal learning. Transformer is used as both the teacher and the student models to learn the latent representations of text, speech, and image. The teacher model uses the transformer to generate a target representation that applied to train the student model. After the full input has been embedded as a sequence of tokens, Data2vec masks a part of the full input by replacing them with the learned mask embedding token and feed the sequence to transformer. At the end of the training, only latent representation learned by the student model is kept, and the learned transformer is used as an encoder for multimodal learning. Data2vec updates the teacher parameters delta through the current teacher parameters delta and the student parameters set by EMA, defined as here and in this figure, where tau linearly increases from tau 0 to the target value TE. At the beginning of training, the teacher is updated more frequently than the student model. Training targets are constructed based on output of top key blocks of the teacher transformer for time steps. Suppose that output of block L at time step t is denoted as ATL, which is normalized in each block to obtain A caret T L. The training target YT is average over the top key blocks, defined as here and explained in this figure. The normalization prevents the mode from collapsing into constant representation for all time steps, and also prevents layers with high norm to dominate the target features. And given contextualized training targets YT and model prediction FT at time step t, a smooth L1 regression loss is defined as here, where beta controls the transition from a squared loss to a L1 loss, which depends on the gap between the target YT and the model prediction FT at time step t. For more details, please check with these references. Thank you. Bye.